So when we look at the introduction of all-flash array, that we find many challenges. Challenges, for example, when we're actually looking at a traditional array, suppose this is our base performance baseline. When we're adding features more and more, it turns out to be we keep getting decreased in performance. So, for example, after we add inline compression, we get percentage off. Then with inline duplication, it's even more. And with snapshot and with metro cluster. So that makes everything worse is the famous that the SSD, the GC kicks in. So what we're trying to address that is using architecture which is optimized in a way that we don't suffer those losses. So when you look at our baseline is with 80% space utilization and with GC kicked in.
So what's GC?
Garbage collection. That means the SSD internal GC. We're also using our the read direct on write so that we don't suffer any performance loss with read 5, read 6 for read TP. TP stands for triple parity. And after we add inline compression, we do have an overhead. And when we add inline deduplication, also have a little bit overhead. Snapshot is free, and metro cluster, a little overhead. So the numbers are to the best of my drawing skill. So these numbers is actually relative true to each other. So
why did the Dorado one start with more
performance?
Yeah.
Yeah, it's because it's all new design in that way.
Can I ask that you speak up a little bit? It's some difficulty here on this side of the table.
Sure. Yeah. So this is our Dorado architecture. It's quite conventional in the sense that we still have the target, replication snapshot, non-management. Then we have cache and the route. After that, below that, we have deduplication engine, compression engine. Then the metadata management. This is where most of the change happens. Then we optimize our data layout to fit SSDs. And underlying, we have a very optimized infrastructure as well. So this is one controller. So every enclosure, we call that engine. It has two controllers inside. Then they're connected using PCI Express, and multiple engines can actually collaborate. We also use PCI Express to connect all the engines. So this is the overview of our architecture. So then I will describe the write flow, read flow. Then I will describe the internal data structures.
Sorry, can you go back? So your engines are connected through PCIe.
Yeah.
And then so that's like within each controller, or the actual engines are?
So when you look at the particular enclosure right there,
Yeah.
the two controllers here
Yeah.
in one enclosure.
Right.
Then when you connect multiple, you use PCIe cables or
Okay.
to connect them.
And the storage is a NVMe storage as well, so it's also PCIe connected to each of the engines.
The drives can be either NVMe or SAS.
Yeah.
Okay. So the write flow is actually really simple. We receive from the user, we mirror to the other side, which is the other controller.
And the cache is
terminate.
non-volatile?
What's that?
The cache is non-volatile?
Cache is non-volatile. It's memory, battery-backed DRAM.
Battery backed DRAM.
Then after we get the cache with dirty data, we now have another step, which is asynchronous, means it's background. We flush those data to SSD. This I'm trying to describe the inline dedupe flow, means we have the data here, we route based on the fingerprint. Then we find the fingerprint shard controller. These two controllers can be the same. Shard means just logically it's a where we find the fingerprint home shard. Then we're trying to compare the fingerprint as well as the data. So if both are matching, we think we find a duplication. So the reason we use this because we're using a weak hash. Then after we get the fingerprint index, we update the non-map shard controller then with the fingerprint index for that particular LBA. And after that, it is flushed.
So the back end is a log structured file system kind of layout, or is it directly addressed?
We use a copy on write on that one.
So
Yes.
from a snapshot perspective, copy on write. Okay.
Yes.
But the back end
It's the row.
devices themselves.
It's directory on.
For Snapshot, it's redirect on right.
Yeah.
Not copy on right.
Yeah.
Sorry.
Okay.
He was there's a miscommunication. He was talking about something other than the snapshot. So snapshot's redirect, not
Yeah.
copy.
All right. So the back end, again, what is the back end? Is it laid out with a physical LUN assigned to a physical SSD, or is it, is it a log structure file system where the data is written sequentially even though it's coming in randomly?
The data layout is, we do also do redirect on write. Means it is we don't erase until we garbage collect. So in a way that it is log structured, but it's not really just one log. It's multiple logs put in that logic.
Couple questions.
Yeah.
So you're flushing out. How often? What triggers the flush? Is it timed? Is it based on watermark?
It's based on watermark and time.
So both, either.
Yeah.
And second, when in the previous screens that you don't have to go back, where the controller had you had PCIe and it was going to PCIe to the other controller.
Yes.
Obviously, there's a card in the PCIe slot, right? What kind of card is in that PCI slot that connects the controllers for high availability?
That's one of this chip.
Oh, is it like InfiniBand or what's the
That's the PCIe.
So you have a PCIe switch or something that's connecting all these together, or do all the
PCI
controllers?
switch.
Yes, it's a switch.
So actually, it's literally PCI to PCI connectivity. Nothing in between. There's no network, no InfiniBand.
No, so the engines are connected together via PCIe switch. So if you only have two engines, you can do point to point. But if there's multiple engines, we have redundant PCIe switches to connect the engines. But in one engine, there's two controllers, so it's the PCIe over the backplane.
Right.
So they're literally the PCI buses are connected without any network port. It's not other controller platforms will have InfiniBand or some other in the PCIe slots, and that's how
Okay, yeah. No, it's PCIe.
You're actually doing it at bus speeds.
Yeah.
Yes.
Yeah, between the controllers.
Oh,
Yes.
wow, that's cool.
Yeah, and I'm surprised you guys didn't ask about NVMe over Fabric earlier.
Well, I mean,
Should we ask about NVMe or whatever?
We assumed there was a slide.
If you're looking at the 18,000 diagram, you can find those ports. In the case of the deduplication is disabled, it's even simpler. We're just looking at the LBA, route to the non-map shard controller and persist over there. I mean, persist flushed over there. So when on the read path, what for a dedupe'd block, by dedupe'd block means when we're actually looking at the non-map. If the non-map is pointing to a fingerprint index, we know that's a dedupe'd block. For that ones, we first route based on the LBA, find the FPI, then use the FPI to route to the physical shard, fingerprint shard. Then we read data and reply to the user. For undedupe'd block, we're looking at LBA, get to the physical address, which is local on this shard. Then we reply to the user. So when we look at our design, there are several things we're trying to maximize our performance. So this is our threading model. What we're trying to achieve with the threading model is to give you the best performance. So here, we employ a share nothing model, which means we partition the data structures into fine shards. Within each fine shards, we can have a shard to core binding or affinity, if you like. There we do the lock-free, even atomic instruction-free operations, so that when we're looking at a particular thread level or task, we use also the non-preemptive lightweight threading, LWTs, so that the tasks are run from beginning to end, so run to complete model. So this will minimize the context switch cost. We also have a highly optimized data path because the SSD is really fast. Here we have optimized data path for read, for compression, and for diff. The technique we're using are we extract common blocks.
Well,
So we don't have to, so that we can save the redundant computation. We also do as much vectorization as we could, so that to extract the instruction level parallelism. We also optimize our branches, for example, here, so that it's become more and more to exploit every possible CPU that we can use. So these are the examples we get from, we can achieve with our data path. So compared to the open source design and the other popular designs, we can achieve something anywhere from 70% to 300%. So for example, the RAID-TP 10+3, we can get 6.5 gigabyte per second with one thread. With algorithm, it's about double the speed of the popular design. We also have 3x design on the diff part.
is that your RAID-TP ratio, 10+3? You don't get bigger than that?
No, this is just when we test it. The TP, user can select the read configuration. User can select. Do I need to stay this a bit longer?
I think I'm good.
Good?
Yeah, I'm good.
Okay. And also, one key point in our all-flash array is the metadata design. The metadata design, we're trying to achieve two objectives. First is optimize for memory so that we can address more flashes. Second one is we try to optimize for parallelism, means we can make it runs faster without step onto each other. So what we're doing here is in our metadata, first is we're trying to do small grain updates. Means that's when you...
So the optimization algorithms that you have there are, because they're shared nothing, multi-core, or is it because you've actually implemented new functionality that's actually faster than the old LZ4, for instance?
We have implemented
new, faster,
new,
more
fast.
efficient. Yeah.
Yes, but not only that, we also shard so that we can shard so that it's shared. It's shared nothing between shards. So that both are actually helping us to get the high performance. Then on these details is we're trying to actually minimize the metadata write amplification. What we're trying to do here is we use a small grain. We also coalescing the updates. So the inner nodes updates are coalesced together. And we also do a prefix B plus tree here, which we can be able to address twice the amount of flash. So in line with this is still it's trying to see that how do we optimize for the parallelism, the non-map. We're actually partitioning them into shards, many shards, so that they are not interfering with each other. The fingerprint, we also
And you're partitioning them in shards because, they're all running on the same engine, right?
Correct.
But it's just the ability not to have it be locked?
That's correct. Because if you look at this design, because we bind each shard to a particular core so that we can actually have a lock-free and atomic instruction-free operation on them.
I got you.
Yeah. So the fingerprint is all sharded multiple buckets, many buckets. Here we have the ability to store variable size fingerprint buckets. This way we can actually resolve the conflict when we're trying to do the hashing. So it's more efficient that way. So here we can see a bucket has a size of 4 entries. Then we can, some bucket will have size of 8. So those are the metadata design, trying to optimize for memory. Sometimes, even we do all this optimization, we still cannot fit everything, because when you look at modern computers, it has a fixed maximum DRAM. So beyond that, you cannot add more. So what we're trying to do here is, with all that memory, we dedicated those memories to cache all the inner nodes. The rest of the memory, we basically will cache the NIF node so that those are cached on demand. So this is another way that we can actually optimize for memory. This way, when we're looking at a particular user access, the user access will only have maximum 2 drive access. This is only when the DRAM is not, it's the maximum that a particular platform can approach. This is another one. This is when we're looking at the data layout. So that's the metadata. Now we're looking transit to the data layout. We're trying to minimize, we're trying to do all these synergies here. For example, here is, when we look at why we do the COW, the log structured. The cost for in-place update is really high if you're looking at an in-place update. So for read 5, you have 2 more read access and 1 more extra write, and total I/O is actually 4. Then extra I/O is 3. So if you look at the IOW design is when we always take one new stripe, then copy the data over. So in this way, when you're looking at read 5, read 6, and read TP, we don't have any extra IOs. So that's the, and also this way is very friendly for SSD, so that it's you can actually utilize all the SSD bandwidth.
Sorry, can you go back to the previous slide? So you're saying that the rate penalty, or rate 5, rate 6, and rate TP is just an extra I/O. Is that what you're saying?
Well, it's just
No,
one
this is
IO
just
because they're
the
writing a whole stripe.
One IO.
Oh,
Because when
okay.
you read,
The log
it basically
structure
goes
file.
here. When you write, you basically take a new one and you write it there.
Okay, yeah.
So that's why that's the
But
basic.
there's garbage collection.
Yeah. So the cost is garbage collection, but yeah.
Okay, got it. Thanks.
So that you can see that with a kilobyte block size and the 100% random address, 7:3 read-write ratio, the cost for the performance for read 5, 6, and TP, they are the same. We also have many things here which we optimize on the layout side. For example, when we're looking at a particular write or implementation doesn't aware the SSD layout, what happens is the user write comes in. This is a time that the write happens. So when you're looking at the write, which realize on the drive, it will be looking like something like this, because the writes are mixed within each block. Here, each block is a flash erase block. That can be very large. Then, when we do the array level GC, the typical method is pick the highest one with garbage percentage, with highest garbage percentage. For example, 94, 95, 93. Here, when we're trying to garbage collect them, we move it somewhere else. Then when you're looking at from drive perspective, we issue the trim to those blocks. The drive, we are looking at something like this. So this way, the drive will still have to do some work to move the data around. So if we have a GC which aware the SSD layout, what could happen is something like this. Data happens, data right here. Now, when we pick the blocks we are trying to garbage collect at array level, not only we're looking at the garbage percentage, we're also looking at the time that the blocks adjacent to each other. So the blocks adjacent to each other in time. Then we can pick those three. When you look at the drive, well, after we issue the trim command, it will be looking like this. Then we have a whole flash erased block which can be reused. So this is one data layout optimization we can use. The other one is the multi-stream SSD. Because the drive we're using is our own drive, so we can actually have this before everyone else is actually jumping into the multi-stream one. So looking at the standard SSD, when the data we realize and we observe, data can have different lifespans. So for example, the red one here have a small, let's say, short lifespan. The data with blue have a longer lifespan. What this means is if we don't do any kind of optimization, when you write to the SSD with standard SSD, what happens is when you look at the drive particular block, after time t, the
So
blocks
as far as
with,
the lifespan is concerned, you're keeping sort of a heat map of block updates?
currently I need to confirm, but I don't believe so.
So I guess the question would become, how do you know that some block has a short lifespan versus a longer lifespan at the time that you're creating the stripe, right?
So I can give you some hint, like, for example, some data we know that the metadata will have shorter lifespan. Some journals will have shorter lifespan. Yeah. And also, some data which you already garbage collected one round and is still alive, they have a longer lifespan. Those kind of ways, without getting into specifics.
Okay.
But you're not writing it.
The lifespan means you either delete or you've been overwritten. So the interval between the two events for a particular LBA, that's the lifespan.
Okay.
So when you're looking at a particular time t, which all the shorter lifespan data is expired, looking at the drive or the flash blocks, you can see that they are everywhere. So reclaim them will cost more, trying to move the data around to get. So when you have multi-stream SSD, what we can do is we put all the blocks into the one stream, the longer ones into other stream, even longer ones into other streams, so that when the block with short lifespan expired, we have a whole flash block ready to be used. So this means the drive will do less work when copying data around. Okay?
When you say a multi-stream SSD, or multi-stream SSD versus a standard SSD, these are ones that you're making, right? You're
We are making this.
right.
Multi-stream SSD. The one that you show,
Right.
you have there, it's capable of multi-streaming.
So are you talking to it through, say, NVMe, through multiple queues, like the 64 queues of NVMe, or is it different than that?
It's a different concept than the multi-queue. Multi-queue means the interface, how much you can actually utilize on the interface level, so pump to different queues. This one means you can somehow tag different address to a different, where I think the drive should understand, then it will be put differently. So it's two concepts,
Oh, it's a different area. Okay.
different area.
I'm still confused on your comment about how you said, how do you know when the data is being written,
You think you need
whether it's going to have a short or a long lifespan? I mean, I understand what you're saying in terms of the collection and if you're moving data, but
330.
how do you know? You're saying you get a write amplification reduction, but I mean the data, you don't. The array is not aware of what the data is, or the disks aren't aware.
Array actually knows. When looking at it, we can first we know that metadata and data. Those are two separate
Okay.
things. And array knows what is journal and what is
They're not
not.
going to go.
So the
And also-
the actual user data would be what you would consider the long lifespan data, and your
The
your
user
metadata.
data can
and
have two categories. First thing is before my array actually doing one round of GC, they are gone. Means they are relatively short lifespan. Or versus some other data which after one round of GC, they're still there. So you need to copy forward, which means in that sense, their lifespan is longer.
So you're moving. So it's not just the new data that you're writing in this example. It's the maintenance of the data that's already.
Yeah, because
there.
the way that we use redirect on write, we also have garbages. If you're looking at this one. Here. The gray ones are garbages, means those three are not garbages. They need to be copied forward when we do the array level GC. And those will have longer lifespan compared to, let's say, 3 here. So that's why we know.
So we might
Yeah, we don't,
not.
currently we are not actually remembering a heat map.
He has 10 slides.
So I mean, garbage collection is an ongoing activity that's happening all the time. As you're writing new stripes, you're collecting old stripes and trying to free them up at the same time. It's not like you have a separate, activity which is just doing garbage collection, distinct from being data written.
So it is a background process, and it's happening all the time. It's just we only do that when we think that the space is.
But you're
we need
creating
to
new
play.
stripes all the time for new
Yeah.
data that comes in.
Right.
It's possible that you could actually be collecting data at the same time, garbage collecting at the same time, and you could take some of those longer-lived blocks and incorporate them with a newer stripe if you wanted to.
You're right. You're right. Yep, that's possible. Yeah, that's possible. But then it's actually mix the new writes with longer living ones. That's
Yeah.
actually defeat purpose of that.
Of trying to optimize
Yeah,
it.
trying to actually separate them. So
All right.
then I'm going to present the test results. Before we go there, I'm going to show why we choose a particular compression ratio and dedupe ratio. So we have 5 column groups here. Each column group representing a particular data with different compression ratio. For example, this one means we have compression completely disabled, regardless of the data. This, we have uncompressible data, means compression ratio is 1:1. We have compression ratio 2:1, 3:1, and 4:1.
These are
with-
different data patterns.
This is just different input data.
Yeah.
Then within each column group, we have different bars. The first bar, the blue bar, means we disable the dedupe. Regardless of the dedupe ratio of the input data, we just turn off the dedupe ability of the array. Then the red bar we have here is the undedupable data. Then the dedupe ratio 2:1 and 3:1. So you can see from here that this is our lowest performing point. So that's why we choose this as our all future slides showing. So we do have global deduplication like we said before. The numbers you can see here is we're trying to limit the latency to be 1 millisecond across. Then we push the I/O to check the maximum IOPS. So here we can see the overhead is about 18%. Because we do redirect on write to have snapshots. So snapshots is relatively free for us. But you can see here with same test configuration, it's basically we don't have any performance loss at all. We also have active metro. Here we do optimization is the optimistic locking. Means we assume we get a lock always. Then if we have an issue, then we back off. So as we can see here, the same configuration test scenario. We have overhead of 16%, but still with all that, we still manage to achieve 280,000 IOPS. We also scale out to the point to achieve high performance. When you look at a particular controller and the resource sharing part of it, these are the non and cache. They are local processes. They actually account for about 20% of all the CPUs. The rest, inline deduplication, inline compression, as well as read, stripe, system GC, multi-stream, all this, are fully leveraging the global resource across all controllers. This accounts for about 80% of the cores. So, currently we have one and two engines and 4 controllers. We can see the scale ratio is around 92%. And as we discussed before, each node can be optimized, configurable as IOPS optimized versus bandwidth optimized. And with our QoS support, we can guarantee the performance of each. Then we can share the same pool down below. So here we can see the performance numbers, which we can achieve the read-write mixed of 330,000 IOPS with 2 controllers, and IOPS is 12 gigabyte per second for reads and 6 gigabyte for writes.